Harvey White, who has worked with Jacobs for more than 30 years, believes Jacobs learned that lesson from his father, who owned a restaurant, the Boston Beef Market, in the family's hometown of New Bedford, Massachusetts. In high school, the younger Jacobs played football and was a sports writer for the school paper, but also excelled at math and made honor society. Expecting to follow in his father's footsteps, young Irwin enrolled in Cornell's School of Hotel Administration, but he quickly gravitated instead to electrical engineering.
I myself was very lucky, actually. Managed to get an excellent engineering education at both Cornell as an undergraduate, then at MIT as a graduate student. In the last term I was at Cornell, one of the last courses I took had to do with the technology of vacuum tubes. And the theory was great, but we also built some vacuum tubes. That hasn't been too useful. Luckily, though, while I was there, I also, of course, took a number of theoretical courses. This was after I left the hotel school and went over to engineering. Indeed, one of our products at Qualcomm had to do with putting a satellite terminal on a truck, using satellites that are not designed for mobile communication, designed for fixed communications. And so how do you design an antenna that will be small, be on a truck, be very reliable? And we sweated over that for quite a while. In fact, I think it was in a discussion trying to explain to financial person Harvey White what the problem was, that in fact the solution came up, and it was based on some things that had learned way back at Cornell in EM theory. So that's one of the reasons someone commented that I always stress that when you're at a university, taking the basic material is the critical part. And indeed, you can never tell where it's going to be useful. But often it's just what you need to make that additional step ahead.
Irwin Jacobs arrived at MIT for graduate school in 1956. He was immediately taken with the new theories of former Bell Labs mathematician Claude Shannon, who was then at MIT, theories that would eventually underpin the science and engineering of the digital communications revolution that Jacobs would harness. Robert Gallagher arrived at MIT that same year.
Both of us, when we got there, were struck by this wonderful, very hot field at that time, which was communication theory. Irwin was one of the few students there who really was torn between statistical communication theory and also this group in processing information, which in a sense was the newer thing at the time.
In 1959, Jacobs received his Ph.D. after completing a thesis that earned him a full-time faculty position at MIT.
So all the rest of us at that time were writing theses about the physical layer of communication. Irwin, as he has done many, many times since then, showed an eagerness to travel the less traveled path. And you know, this one was so beautifully organized and so beautifully put together that you could sit there and read it and be fascinated by it and say, gee, that's really interesting. It's really neat stuff.
Even then, as Gallagher highlights while reading from the thesis, Jacobs was taken with the concept of communication networks.
A probabilistic graph is a linear graph in which both nodes and links are subject to random erasure. Such a graph may be thought of as an idealized model of a communication network.
From 59 to 1966, Jacobs was on the faculty at MIT.
Irwin, at that time, being encouraged to go into practical things, went into taking over some labs, teaching laboratories, teaching an undergraduate course in communication, doing consulting at Sylvania and at Lincoln Lab on very new and interesting communication systems. The most interesting thing he did at that time, and the thing which has lasted the most, is the book. It was called Principles of Communication Engineering.
Co-written with fellow MIT professor Jack Wozencraft, the book grew out of class notes that the two wrote for a course in communications engineering.
Lots of books are called principles. Very, very few are. This, in fact, was a book on the principles of communication. It is still the Bible of many, many very good communication engineers. Perhaps most good communication engineers regard this as the true way of looking at communication systems. They took the best part of information theory, the best part of the new parts of communication theory, put them all together into something which could be called an engineering textbook. And I claim that all of the things that Irwin has done since then, if you look at the major systems he's been the architect of since then, and you look at the various pieces of them, all of them come from this inordinately deep appreciation he had of what all this theory was all about.
For all these decades, the theory has held good. And Irwin's book, Principles of, held good for decades. I mean, that's incredible in a textbook. The rise of wireless, aided very much by Qualcomm and Irwin, has kept communication theory alive.
In 1964, Jacobs began planning a sabbatical from MIT and explored possibilities on the West Coast. A fellow communications theorist, Andrew Viterbi, was part of a very active group at NASA's Jet Propulsion Laboratory in Pasadena during the heady days of the space program.
He asked me whether there was a position that might be available, and so I passed on the word with obviously a very strong recommendation. And then Human Resources followed up the application and sent him a rejection letter. We rapidly straightened that out, and Irwin spent a very productive year, and that certainly whetted his appetite for a permanent position in the West.
A former professor at Cornell, Henry Booker, was hiring faculty for the University of California's new campus in San Diego.
Henry Booker was a professor of electromagnetic theory. He was the one who came to UCSD to start what was then called the Department of Electrophysics, and which became now electrical engineering, computer engineering. But I took a very good course in EM theory from him, and he gave lots of insights into there's lots of equations, and you can do great calculations on, well, sometimes you can, sometimes you have to simulate it, but there's a lot of very good theory there, but he'd give you a very good feeling for it, a gut feeling for what can be done, what can't be done. And so that's lasted ever since.